Hi everybody. In this section, we're going to keep going with Chapter 2. We're going to do a little bit of calculator work today. Nothing too serious, but I'm leaving it up there. So not a ton of calculator work, but you're going to want to have it handy for some of the examples. So let's jump right in on section 2.2. Alrighty, so in this section, we are going to look at graphs that describe one quantitative variable. So this section is mostly just about graphs. We look at some other features as well, but we're going to look at the general shape of data for a quantitative data set, where are the data values centered, and how do the data vary. And these are all aspects of what we call the data distribution. So quantitative variables are very different than categorical variables. When we have a categorical variable, the bar chart is the only way to display that data. Bar charts and pie charts. Here we're going to have lots of ways to display quantitative variables. So we're going to do the first two bullets in this section, and the third bullet is the next section. And so the most common graphs for quantitative data are this dot plot, histogram, and then a box plot. So let's see how this works. So let's look at a dot plot first. So here is a random sample of 111 Honda Civics for sale in the Cleveland area in 2016. So this is something you might be interested in. What's the distribution of prices of these used cars? And you can see that each data value appears as a dot. So there's 111 dots on the graph. And if multiple data values are the same or almost the same, then they're stacked up. So you can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 cars, 11 Honda Civics, right around $15,000. But there's only one just above $15,000. Right, so this is a good way of understanding the distribution of a quantitative variable. And it's easy to see any data values which may be far from the others. These are called outliers. So these are what we call unusual values, and we just call them outliers. So here's a Honda Civic that in 2016 was for sale, and it cost over $21,000. So that's got to be a very fancy Honda Civic for sure to cost that much. And over here's one that costs around $2,000. Not very fancy. But these values are not very close to most of the other values, right? The other values are mostly clustered in this area. So we want to think about anyway, values that are far away from the others. Those are called outliers. And the idea is that the outlier is notably distinct from the other values. Usually an outlier is much larger or much smaller than the rest of the data values. For stuff in this section and the next two sections, all outliers will be too large or too small compared to the other ones. And identification of outliers is important for many reasons, including identifying potential data input errors. So if you were looking at this graph and you saw one of these big numbers and you said, oh, there's no way a Honda Civic costs that much, that's got to be a mistake. If you were using this data for some sort of publication, you'd have to go back and double check that data value because it could mess up your results if it indeed is a data entry error. Maybe the data said $22,000 and in actuality it should have said $2,200. Somebody just typed an extra zero. But when you're doing statistical analysis, an extra zero can make a big difference, right? So that's why we look for outliers. It's one of the reasons, but it's the main reason. So here's what we call a histogram. Same data set, all the Honda Civics. And you can see that it looks like a dot plot, but it doesn't have as much detail as a dot plot. So the way we make a histogram is we take the quantitative data values and we place them in buckets or bins. Then the number of values in each bucket is counted. The count determines the height of each bar. So here, if you look back, there were 111 cars or Honda Civics in this data set. Here you can see exactly how many fall in each category. So this graph has 6 buckets, 0 to 2000. And you can see it looks like only one car was in that category. 2001 to 6000, that's this one. You can see about 17 cars were in that category. So histograms are really nice for seeing the general shape of the distribution, but they don't give you as much detail as a dot plot. Sometimes you want to see details, sometimes you want to see the general shape. It just depends on what you're studying. And when we consider the general shape of a distribution, we ask ourselves a few questions. Is the data set approximately symmetric? And if it's not symmetric, is the data piled up on one side? And are there outliers? So one way to answer this question is to smooth our histogram into just a curve. Just chop off all the rough edges and smooth it down, like you're sculpting it or something, and it helps see the general shape. So if your histogram looks like this, with a lot of spikes and a lot of pokey bits, maybe it's hard to see the general shape. You might want to replace that with this smooth approximation, just because many times in statistics we're interested in the general trends and which direction the data is pointing and things like that. We'll put names to all this stuff really soon. But just trying to give you a general idea what's going on here. So if the data is piled up on one side or the other, then we say that it is skewed to the other side. So this graph here is skewed to the right because it's all piled up on the left. That's similar to this one here, right? So if you see a smooth curve like this, just try to imagine a histogram that looks the same way. Well, we have a whole bunch of data piled up here, and then as the variable increases, the frequency in that bin or that bucket decreases. So this is skewed right because it's piled up on the left. Well, this one over here is exactly the opposite, right? It's piled up on the right, so it's skewed to the left. The distributions are skewed towards outliers. So the idea is that, and I'm going to go back one slide again, think about data values that are way out here. It's not really close to most of the other data values, so it could be an outlier. Well, outliers, by definition, mean that there's not very many of them because they're far away from the majority of the data values. So if it's piled up on the left, it has to be skewed to the right, and therefore the outliers have to be on the right side. So if there are unusual data values hanging around, they're going to be on this side for something skewed to the right. If a data set is skewed to the left, then the outliers would have to be over here on the left side. And that's just a definition, okay? That's just a rule. So you have to remember this, and if you're not sure which one's which, look for the big piles. The skew goes the other way, which means the outliers go the other way, because outliers can't be next to the big piles. That's the easiest way to remember it. So if a distribution is symmetric, it just means the left and right sides are mirror images of each other. So here, this is symmetric, because if you draw a line right down the middle, you can fold it in half and the edges will match up, right? It's a mirror image. Same thing here, right? If we draw a line down the middle and fold it up, left and right sides are mirror images. So these are both symmetric, but this one looks like a bell, so we say it's bell-shaped. This one doesn't look like a bell, so we say it's not bell-shaped. So it turns out that this slide and the previous slide are the only 4 cases you need to be responsible for in this class. Skewed right or skewed left, symmetric and bell-shaped, or symmetric and not bell-shaped. That's it. In other words, if it's not symmetric, it's automatically not bell-shaped. So you don't even need to say that. If it's not symmetric, it's probably skewed to the left or skewed to the right. So essentially, every graph that we're going to see, we're going to force it into one of these four categories. And what you're going to notice as we go through the class is that a lot of the graphs that will pop up in our computer simulations just naturally look like one of these four. This is sort of a naturally occurring thing when you start to look at data. So, skewed left, skewed right, symmetric bell-shaped, symmetric not bell-shaped. That's it. So here we have some distributions. And again, just ask yourself, skewed, yes or no? Well, this one doesn't look skewed, which means it's symmetric. Does it look bell-shaped? Sure does. So that one's symmetric and bell-shaped. It doesn't have to be perfect. Remember, we're smoothing off those rough edges. Just imagine it's made of clay and we're just going to push down the rough edges and smooth it out. That's it. What about here? Well, it doesn't look symmetric because we can see that there's nowhere you can draw a line and then fold up the edges to get them to match up. So that means it's skewed to the left or skewed to the right. Well, it's piled up here on the left, which means it's skewed to the right. And that's it. That's all you're going to have to do for general identification of shapes of distributions in this class. We don't go into any more detail than that. So let's look at the center of the distribution. So we talked about the shape, now we're going to talk about the center. So the center of a distribution is what a typical data value will look like. And these are described using general concepts such as center or average of a data set. Two summary statistics that describe the center of a distribution for a single quantitative variable are the mean and the median. So just imagine any quantitative data set. Imagine you have a sample of college students and you want to know what's the average height. Well, why do we want to know the average height? Because that's a typical observation. So in order to learn something about a population, you need to know what a typical observation looks like. And we describe that with the center. So like a representative observation, right? Or we just use average. So our first measure of center is the mean, and it's the numerical average. When most people say average, in most cases, they're talking about the mean. And the mean is just the sum of all the data values divided by the total number of data values. There is a mathematical way to write it. I went ahead and put that at the bottom because some of the more mathematical things do come up from time to time. And so you should get used to seeing these symbols because they do come up. So these x1, x2, xn, these are the data values, and the Greek capital letter sigma here tells us to sum the values. Right, so the sum of all the data values is just x1 plus x2 all the way up to xn. Remember, there's only n data values in a sample. And of course, the total number of data values is, of course, n. That's the sample size. And this is the shorthand way to write it. So let's see how to do this. But before we compute more stuff, we want to talk about notation. Just like in the previous section, where we had separate notation for sample statistics and population numbers, we have the same thing here. You just have to memorize this stuff. You will see these two symbols 1,000 times this semester. No exaggeration. So a sample mean is denoted x bar. So it's not x hat. P hat was in the previous section. This is x bar. And the population mean we call mu. So that is a Greek lowercase m, and it's pronounced like the noise that a cat makes. Okay? You cannot write the letter M for mu because we use that letter for something else. So summarize or compute each of the following using appropriate notation. So we want to decide, does this number come from a sample or a population? The average number of TV sets in the US is 2.6 per household. So does that come from a sample or a population? Well, you can see we're talking about in the US. So it says the average number in the United States. Well, that's a large population. So that means this is going to get the symbol mu. So we're going to write mu equals 2.6 television sets, or you can write it in words. Both of these are acceptable. If I ask you to use the symbol, please write the appropriate symbol. So these two things are saying the same thing, right? When we say there are 2.6 TV sets per household, that just means on average, right? That doesn't mean everybody has 2 TV sets and then 6/10 of a TV set sitting around, right? This means on average. So that symbol with the number and the sentence mean the same thing. So let's go look at part B. A random sample of 5 households in Ohio yields the following data on the number of TVs in each one. So this is clearly a sample. So we're going to attach the symbol X bar to this. But let's go back one more slide. Okay, so we have X bar, but let's look at what this mean is. It's the sum of all the data values divided by the total number of data values. All right, so we have to sum up these data values. So that's one of the few things we need the calculator for today. Oh, you know what? I want to point out something real quick. So I had a student ask about this. Can't remember if it was in a discussion forum or an email. In my previous video, I showed you how to type in fractions that are stacked, and sometimes when you type them in stacked, it wasn't translating properly. If that's happening to you, here's how you fix it. Go to Mode, and then every calculator is a little bit different, but you're going to go to Answers. You're going to go to where it says Answers, and you're going to force it into decimal mode. This should work for everything you have to do in this class. So if yours says auto or frac for answers, you want to force it into decimal mode. That will fix that problem that I showed last time. So I went ahead and forced my calculator into decimal mode. Now I can type in stacked fractions. Some people prefer everything as fractions, but on your homework it's a lot of decimals, so let's convert everything to decimals. So here's my fraction, right? You just go, alpha y equals. So then I'm just going to use the formula. So it's 6 plus 3 plus 1 plus 5 plus 2. So it's the sum of all the data values divided by the total number. So there's 5 data values. So I'm just going to put in 5. And that's it. That's your answer. Don't forget to use the appropriate symbol. The homework does not require you use the symbols. On a test, I could require that you use the symbols. So there are 3.4 TV sets per household in the sample. So here we have the nationwide average. That is some sort of known value. And we have a sample in Ohio that represents a different population. Assuming it's a random sample, right? All right, let's keep rolling. Next up, the median. So the sample median is denoted with the letter M. That's why you can't use the letter M for mu. You have to use that funny symbol. So you should practice writing it because it will be required on exams. It is the middle value. So this median is the middle value or values. A median can be more than one value. In a quantitative data set, once the data values are arranged in ascending order. So in order to compute a median, you have to rewrite all the data values, lowest to highest. If the number of data values is odd, then the median is just the middle number. That makes sense, right? Because the sample median is the middle. So median and middle have the same meaning. If the number of data values is even, the median is the mean of the two middle numbers. So I'm going to show you how to do that. That can be a little bit confusing, but you're not going to be computing this stuff by hand very much. This section is the only section that we compute this stuff by hand. I will not require you to compute a mean or a median by hand in this class on an exam. You might have to label them with the right notation, x bar or mu or m, but I will not require you, and it won't be on the final exam either. You do not have to do these calculations by hand. I just explain how to do it by hand so that you understand what it is. In the next section, we learn a very fast method where the graphing calculator computes everything for you. Compute the sample mean and median of each of the following data sets. So these are both samples, right? In fact, part A here, we recognize that as the sample we just had in the previous problem. So if we're gonna compute the sample mean of this, we already did that, it's 3.4. Let's compute the sample median of this first data set. So in order to compute a median, I put the data values in order. 1, 2, 3, 5, 6. Then you just choose the middle number. In this case, it's 3. So the median is 3. Pretty easy stuff. Let's look at part B. In part B, it's almost the same data set, but it's a little bit different. Let's compute the mean of this data set. So I don't want to type all this in again, so I'm going to go second entry. It retypes it for me and allows me to edit it. And then I'm just going to hit the back arrow until I get back in the top. And then I'm just going to type plus 100. Now I have to change the bottom number to a 6 because I don't have 5 data values anymore. Now I have 6. And now my mean is 19.5. Right? To compute the median, I just write 1, 2, 3, 5, 6, 100. And there are 2 middle numbers now because I have an even amount of data values. So I have to average the 2 that are closest to the middle. And the median is then the mean of 3 and 5. So 3 plus 5 is 8, divided by 2 is 4. So 4 is the median. And then question C, so part C asks, did these numbers change very much when the outlier was added, right? Let's go back and look at it, exactly what it says here. Nope, that's what it said. Yep, did either the mean or median change much when the outlier data value was added? So you could imagine that these are something like, I don't know, these are the prices for lemons at a grocery store, right? Maybe this is a really nice lemon. And somebody has a $100 lemon. Well, you wouldn't expect to pay $100 for a lemon, right? So what happens to the average? Well, here the average lemon price was $3.40 and the median is 3. When we added the outlier, the average goes up to $19.50 per lemon. That's awfully high. But notice the median doesn't change very much. So it turns out that the mean changes a very large amount. It went from 3.4 to 19.5. Adding an outlier as extreme as 100 really moved that mean closer to the outlier. The median only changed a little bit from 3 to 4. It turns out that I could put any number in this data set bigger than 6, and that median will change from 3 to 4 because the median is just the middle number. So what's going on here? Why is the mean changing so much? We saw that the median is never going to change very much because it's only dependent on 3 or 3 and 5. So what's going on that causes the mean to change so much? So I want you guys to think about that. Could appear during an exam review, could appear on a test. Think about exactly what is causing the mean to change so much when that outlier is added. And so that brings us to the idea of resistance. A statistic is said to be resistant if it is relatively unaffected by outliers. So we saw that the median didn't change very much when that outlier was added, so it's resistant. The mean changed a lot, so it's not resistant. And because outliers can greatly affect the mean, but not the median, skewed distributions have their mean pulled toward the direction of skew. So that's an important point. And if we go back and look at the answers here, it kind of makes sense. Earlier, we said that outliers will cause a distribution to be skewed towards the outlier. So that means that the mean is getting pulled towards the outlier. Okay, so that should make sense. Whereas the median isn't changing very much. So the median really doesn't get pulled much either way, depending on where the outliers are. But the mean is going to change. And so that means the mean is pulled towards the direction of skew. So outliers create skew. Outliers pull the mean, as we just saw. So the mean and the skew will move together. Now, here's another factual piece of information about the mean. The mean is actually what we call the balance point of the data. So looking at a dot plot or histogram of a data set, the mean is the balance point. What that is saying is that if you had a histogram or a dot plot and it had like some weight to it, like imagine this was made of wood or something and you were trying to balance it. If these are stacked up pieces of wood or blocks and you wanted to balance this thing, it would actually balance at the exact point that is what we call the mean of the data set. This always happens. If you've taken physics, maybe you've seen it if you took high school physics. This is actually something that comes up in high school physics. Or college physics. I know some of you guys are science majors or post-bac. So let's see how to use the relationship between the mean and the median to solve a problem. So I'm not expressing this as like an example. I just want to show it as a trick, okay? This isn't something that you absolutely need to know how to do, but if you know how to do it, it's going to save you a lot of work on your homework. So let's say I ask you to estimate where the mean is. Or I say something like, which whole number is the mean closest to? Well, you just think about where it would balance. So if this thing is made of, I don't know, blocks or something, and it's just like a physical structure, we try to balance it. What happens if I try to balance it at 4? If I try to balance it at 4, it's going to tip towards the smaller numbers because there's too much stuff over there. What happens if I try to balance it at the number 1? Well, there's a lot of observations at 1, but there's too many over here on the right side. It's like a teeter-totter effect. These observations over here will counteract and pull the distribution back to the right. So it turns out the mean is very close to 2. The mean is actually 1.727. If this is a test question, it would be estimate the mean, and you just got to get close to get points, or it'll be pick the whole number that is closest to the mean. So the answer here would be 2, right? 2 is the whole number closest to the mean. Now what do we do with this? Well, if we know the mean is here, the mean is pulled towards the outliers that are over here. So we know the median has to be to the left of the mean. So the median has to be over here. And then here's the trick. The trick is the median uses at most, what we saw in a previous example, uses at most 1 data value or 2. So the median is either a 0, a 1, or the average of one of these. So you can see that this stack of 1s here is bigger than all of these stacked up and this stacked on here. So that middle data value actually is in that stack of ones. So the median is 1. This is actually a very powerful tool, being able to use this. It's hard to do, it takes a lot of practice, and we don't have a ton of time in a class like this to goof with this stuff. I wish we did, but there's no investigative lab component. All the labs you have to do are more using lots of data to answer a question. We don't really have time in a class like this to do investigative labs. But I just want you to understand that it should be believable. So if I give you the median, you should be able to find the mean or estimate it. If I give you a graph, you should be able to find the mean and the median to the nearest whole number. In this case, the median, all of these data values are whole numbers, so the median is going to be a whole number. And that brings us to, how do we visualize the mean and the median? So this is a summary of what we've just talked about, that the mean is pulled towards the skew. So there are 3 possible cases. If a distribution is skewed left, that means the outliers are on the left. The outliers on the left pull the mean closer to those outliers, which means that this mean is less than the median because it's pulled to the left. Remember, the bottom axis is a number line for all of these graphs. These are either histograms or dot plots. It's a quantitative variable, so that's a number line at the bottom. If the distribution is skewed right, the outliers are on the right, which pulls the mean closer to the outliers, and so the mean is greater than the median. If your distribution is symmetric, there's either no outliers, so X bar and M are close together, or there's outliers on both sides equally because it's a mirror image, in which case X bar doesn't get pulled one way or the other, it stays right in the middle. This is what we want to use to get work done in a class like this. We're going to use technology to compute X bar and M, and then we're just going to look at what we've computed to learn about the distribution. This is the best way to learn stats. We don't want to compute a bunch of stuff by hand, and in this class we eventually do, but at this stage we don't want to. We'll do a few calculations by hand, a few small ones, but we're going to let our calculators and computers do the work. So that's it for this section. But before we go, just want to say that here's the concepts to remember. Lots of stuff on there. Make sure you know these concepts before you try to study for a test or something. There's some book exercises here for you. And I want to point out something from your online homework. The last video was really long, so I didn't get to one of the problems. I'm going to do this problem first, and then I'm going to go back at the very end of the video and cover something that I meant to cover in section 2.1, but the video was already 45 minutes long, so I didn't want to extend it out past that. All right, so let's read what this problem, so this is number 12. This is 2.2, number 12. I'm not going to do the whole problem. I'm just going to point out how you want to do it. Okay, and then I'm going to point out things that students get wrong when they try to do it. Please don't do any of these things. Life expectancy for all the different countries in the world, let me make this a little bigger. There we go. Life expectancy for all the different countries in the world ranges from a low end of only 45.6 years in Sierra Leone to a high of 83.8 years in Hong Kong. Life expectancies are clustered at the high end, with about half of all the countries having a life expectancy between about 74 and the maximum of 83.8. A few countries, such as Sierra Leone, have a very low life expectancy. The full data set is provided here. So, let me just point out a couple of things that you got to remember. Number 1, it says click here for the data set associated with this question. If you follow this link, let me show you what happens. Okay? It takes you here to this page that just has all kinds of stuff, right? And it's called life expectancies, so you can scroll down and look at it, right? So you can scroll down. I think that's what it's called. Oh, it's called all countries. Yeah, it's called all countries right here. But here's the thing. We use StatKey for this type of problem. You never need to visit this page, ever in the entire class. Let me say it again. Do not ever visit this page. And if you do, you might as well just click here on StatKey, because once you go to StatKey, every problem in this course that is not part of a lab is already included in the StatKey built-in datasets. You never need to enter a custom dataset unless you're doing a lab. If it is a homework problem, you can either attempt to do the problem without StatKey, or you can use StatKey. I'm going to do a full video of just StatKey, but I just want to point out, because students see click here and they think like that's going to solve the problem for them, and that's not how this works. Just because it says click there, that doesn't mean that that's how you solve it, right? You can solve this problem without StatKey. Look at what it says. What is the shape of the distribution of life expectancies for all countries? Well, think about what you're told. Figure out where the mean and median are. Life expectancies are clustered at the high end. If you have a cluster of values somewhere, what does that tell you about the skew? Right? Think about it. Use the information that's given. Don't think that you need to do something else. These problems are designed to use the tools that are taught in the section. If you need to use StatKey, I'll show you how to do it when it's appropriate, but you don't need it for this problem. Okay? Now it says estimate the median of the life expectancies. Well, think about it. You have enough information right here to do it. So life expectancies are clustered at the high end. That tells you about the skew. Then it says about half of all the countries have a life expectancy between 74 and 83.8. So if half of the countries have a life expectancy in a certain range, what do you think the median is? You're given all the information you need. Okay? And then it says, will the mean be larger or smaller than the median? This follows directly from your answer for part A. Once you solve part A, you can do part C. So I'm not telling you the answer, and I'm telling you that if you choose to click on StatKey, which you're allowed to do, it takes you here. But I'm not ready to show you guys a bunch of StatKey stuff yet. If you want to mess around in StatKey and just click around, that's totally fine. We are doing one quantitative variable. Your data set will be built into the statistics, right? And it's called actually, this one's not even in here. So you don't even use StatKey for this because it's not even in here. This problem you're supposed to solve without using StatKey. Okay? So I know it looks like you're supposed to use StatKey because it says click here. I put this problem in the homework so that you can do it by just using what's given. You're gonna have to be able to deal with incomplete information. All right, so that's how you do this problem. I didn't tell you the answers, but that's how you do it. All right, now I want to show you something else. Let's hope we don't go over time on this video. All right, we got a couple minutes left. In section 2.1, there's one problem that you do need StatKey for. And again, I meant to show you last video, but we just went over on time. I don't remember if it's the last one. Let me see here. Yeah, here it is. It's number 13. Okay. So it says click here for the data set associated with this question. Click here for StatKey. In this problem, you are not given enough information to solve this without either looking at the data or using StatKey. You have to do one of the two. So the restaurant tips data set comes from a sample of 157 bills at a small bistro or wine bar. 3 different servers, A, B, and C, worked on nights the bills were collected. Use StatKey or other technology to find the relative frequency. So look here, in the problem it says use StatKey. If it says in the problem to use StatKey, then you have to use it. That problem we saw in section 2.2 in the quantitative variable section, it did not say to use StatKey. So just because it says click here, that doesn't mean you click here. All right. Now you're allowed to click here to access StatKey as well. Okay. If you want to find StatKey through other means, because there are times you might just want to log into StatKey, you can just Google StatKey, or I put the URL link in the syllabus. You don't have to use the link in the homework. Okay. So when you click on StatKey, it looks like this. In section 2.1, we were doing categorical variables, right? But think about what it's saying here, right? We want to find the server who had the least bills. So the servers are not the cases. In this case, each bill is its own case, because look what it says. A sample of 157 bills. That means the bills themselves are what is being analyzed. So every bill has its own dollar amount, credit or cash, server, tip amount, tip percentage, right? There's characteristics of each bill. So the servers are variables. That means, oh wait, where'd my StatKey go? That means you have to click on 2 categorical variables, right? So we're doing restaurants. Where'd it go? Oh, I lost it. We're doing restaurants. Restaurant server, here it is. Right, so even though server is a variable, we're treating the servers as a case just for this homework problem. So it is in one categorical variable. That's why I'm going over it. This problem gives people trouble. It gave me trouble. And so let's look at what the homework question is asking us now. Find the relative frequency for the server who had the least bills. So which server, collected the fewest bills? Well, you can see the proportion right here. You can use the graph. There's a bar chart, or you can see real clearly the proportions here. So you can see that server C only had about 20% of the bills. So that's 0.204. And so that's how you do that problem. You just open StatKey. You might have to look around in the variables. Okay? So again, going back, you might have to, so section 2.1 had problems with 1 categorical variable and with 2. So you might have to click around in the topics covered in the section to figure it out. But every data set in every homework problem that needs StatKey is in here somewhere. Restaurant server, there you go, and you're all set. All right, well that's it. That's how you do this. I keep doing that. All right, and you're good to go. So if you have any further questions, let me know. I think I covered everything here. Yep, sure did. Next video will be section 2.3. And until then, study hard and let me know if you have any questions. And I'll see you next video. Bye-bye now.